Good day to all of you. We have started studying database management systems. In that, today we shall study chapter 14, Basics of Functional Dependencies and Normalization for Relational Databases. Our sincere acknowledgement and thanks to authors Ramesh Elmasri and Shamkant B. Nabate, authors of the textbook with title Fundamentals of Database Systems. Relational database design means designing which all tables are required and how they must be related to one another. That is first point. And in each table which all attributes or column names must be there and of what data type. So with this set of tables or relations, the data which is available in that application is preserved with minimum redundancy. So relational database design ultimately produces set of relations. Its goal is to preserve the information and minimize the redundancy. So minimizing redundancy means reducing storage of same information multiple times. When redundancy is reduced, storage space required is also reduced and number of updates required is also reduced. When number of updates is less, in lesser number of updates wherever it is required, the data can be stored correctly, which maintains the consistency of data. Means in all multiple copies of data, the same data which is correct, that is available, that is called as consistency. So whenever relations are designed for an application in the relational database design, there must be some measure to check the goodness of quality of relations. Okay. Next, informal design guidelines for relation schemas. There are 4 informal guidelines which are used as measures to determine the quality of relational schema design. In that first one, make sure that the semantics of the attributes is clear in the schema. Second one, reducing the redundant information in tuples. Third one, reducing the null values in tuples. Fourth one, disallowing the possibility of generating spurious tuples. These measures are not always independent of one another. So these are the 4 guidelines which are used as measure to determine the quality of relation schema design. That is, whether the relations designed for an application in a database, are they of good quality, yes or no. To decide that, these guidelines are used. The first guideline is with respect to imparting clear semantics to attributes in relations. So in relations, there will be attributes, means which are the column names in the relation or table. They must be having clear meaning. That is what is imparting clear semantics to attributes in relations. Okay. So the guideline 1 is as follows. Design a relation schema so that it is easy to explain its meaning. Don't combine attributes from multiple entity types and relationship types into a single relation. Intuitively, if a relation schema corresponds to one entity type or one relationship type, it is straightforward to explain its meaning. Otherwise, if the relation corresponds to a mixture of multiple entities and relationships, semantic ambiguities will result and the relation cannot be easily explained. In simple words, this guideline 1 states that one relation schema should correspond to one entity type. That is, in real world we have many different objects. These objects are called as entities. Objects of similar type, to identify them, entity type is formed. For example, employee entity type, department entity type, student entity type. So there will be many employees, but all the employees have same properties. So the properties means their name, their social security number, their salary. So the properties are the attributes of that entity type. So all the entities having the same properties belong to one entity type. So while designing relations, one relation should have the attributes of only one entity type That is, in one relation there should not be mix of, for example, employee entity type and department entity type. If in one relation, if there are attributes of only one entity type, then it can give clear semantics or meanings to attributes in relations. That is what is the meaning of guideline 1. This figure shows a set of relation schemas which are formed according to guideline 1. So, for example, employee relation schema, e-name, SSN, B-date, address, D number. These are the attributes. These all belong to the properties of employee entity type only, because e-name means employee name. This is employee social security number, birth date of employee, address of employee, and department number to which that employee belongs to. So in this relation schema, only one entity type related attributes are grouped. Hence it is easy to explain the meaning of attributes in this relation schema. Similarly, in all other relation schemas, it is easy to explain the meaning of attributes because they are grouping the attributes belonging to only one entity type or one relationship type. So this belongs to department entity type, this one project entity type, and here department locations entity type. Only this works on belongs to one relationship type. Its attributes are social security number of the employee, project number on which that employee works, and for how many hours that employee works on that project number. So this relation schema stores all the attributes of only one relationship type. So this example set of relation schema illustrates how easy it is to explain semantics of attributes in a relation schema if relation schema is made to group attributes of only one entity type or only one relationship type according to guideline 1. Okay. In this set of all relation schemas, how employee, department, project, department locations, relations belong to entity types, and only this works on relation belongs to relationship type. For that you can refer to my previous video on chapter 3, that is data modeling using entity relationship model or ER model. Okay. This is the set of relations which correspond to the set of relation schemas just now we discussed. It shows the database state here. State means set of values stored in each relation. Okay. Next we shall see if guideline 1 is violated, what happens through some examples. For that, let us consider two example relation schemas. The first one EMP underscore DEPT, second one EMP underscore PROJ. If we consider first relation schema, that is EMP underscore DEPT, it is the mix of attributes of two entity types. One is employee entity type and another one department entity type. E-name, SSN, B-date, address, D number attributes belong to employee entity type. E-name attribute indicates employee name. SSN indicates employee social security number. B-date indicates employee's birth date. Address indicates employee's address. D number indicates the department number in which that employee works. So from here to here we have attributes belonging to employee entity type. D number, D name, DMGR underscore SSN are the attributes belonging to department entity type. D number means department number. D name attribute indicates department name. DMGR underscore SSN attribute indicates the manager's social security number. So from here to here, three attributes belong to department entity type. In all, we can say that this EMP underscore DEPT relation schema belongs to two entity types. It is mixing the attributes of two entity types, and hence it is violating the guideline 1. Next, if you consider second relation schema, that is EMP underscore PROJ, it is mixing the attributes of two entity types, that is employee and project. SSN and ename attribute belong to employee entity type. SSN attribute indicates social security number of an employee. Ename indicates name of that employee. P number, P name, P location and hours, these four attributes belong to project entity type. Such relation schemas which are violating guideline 1 have some hidden problems. They are called as update anomalies. These can be used as views but not as base relations. Okay. So what are those hidden problems if we use relation schemas which violate guideline 1? And those problems being called as update anomalies, that we shall see next. Okay. So considering EMP underscore DEPT relation state means the set of values stored for all the attributes in all the rows in this relation. So ename, SSN, bdate, address and D number attributes belong to employee entity type. Okay, this we have already discussed. D number, D name and MGR SSN. These three attributes belong to department entity type. Now there are 8 rows of data in this relation, and in every row of data for an employee for which department he works for, D name and MGR SSN values are also stored in that one row. So for every row here, the values of these two attributes are to be repeated. So this is the block of redundant data. Okay. That is for a particular department number. Instead of storing only once the department name and the department's manager's social security number, it is repeated as many times that department number is there for a tuple. Okay, so this block is showing redundant information. So this problem occurs when a relation schema violates guideline 1, that which mixes the attributes of more than one entity type. Okay, but if you consider employee and department relations, here state is shown, but structure, if you see the employee relation schema which is not violating guideline 1 here, this employee relation schema is having only attributes belonging to employee entity type. So ename, SSN, bdate, address, D number. These are the attributes present in this employee relation schema. So it is not violating guideline 1. So here in every row for employee data, if you see D number is taken for which that employee works, but corresponding department details is stored in department relation. So for department number, that is D number 5, what is the department name and what is the social security number of that department manager is stored only once. Such relation schema which are not mixing attributes of multiple entity types and hence not violating guideline 1 will be free from the problem of redundancy. Okay. Similarly, if you consider EMP underscore proj relation, so here SSN, P number, hours attributes indicate the social security number of employee, the project number on which that employee is working and for how many hours. But every time whenever we mention this, what is the name of that employee has to be repeated, because this employee is working on two projects here and for how many hours that has to be mentioned here, but both the times for the same employee two times the name is repeated. So this part is showing the repetition of ename. Then project number here means which project, that project name, and what is the location of that, so that has to be repeated. So this is also redundant information. For every project number, that has to be repeated. Now instead of EMP proj relation, consider three relations which are not violating guideline 1. The first one, employee, project and works on relations. So the relation schemas of these, if you see, employee relation schema has the attributes E name, SSN, B date, address and D number, the department number to which the employee belongs to. All these attributes belong to only one entity type, that is employee. Here P name, P number, P location and D num, the department number which controls the project. All these attributes belong to only one entity type, that is project. In works on relation schema, SSN, P number and hours, all the three attributes belong to only one relationship type, that is works on. So here in all the three relation schemas, here there is no mix of two entity types attributes or two relationship type attributes. These are not violating guideline 1. Next, if you see to corresponding relation state, means the value stored in the three relations. First, if you take employee relation here, any SSN value if you take, that is social security number of employee. Employee name is stored only once, it is not repeated, there is no redundancy of employee name like how it was there in EMP underscore proj relation. That is first point. Next, SSN value if you take in works on relation, there what project number that employee works on, that is given and for how many hours. For this project number, what is the project name? So for that project number, what is the project name and project location and controlling department is stored only once, there is no duplication of that. Here also there is no duplication of E name, here there is no duplication of P name, P location and D num. So there is no redundancy here. Okay. So this way relation schemas which are not violating guideline 1, their relations will not have any storage of redundant data. They will be free from the problem of redundancy. Okay. EMP underscore DEPT relation cannot be used as base relation because it is having redundancy problem. Base relation means this way it is not stored in the computer storage medium. Instead of that, employee relation and department relation which were free from redundancy problem, which were not violating guideline 1, in that form it is stored onto the computer storage medium, and from that combining the two relations, that is obtaining the natural join of those two relations, this EMP underscore DEPT is obtained for only view purpose, only for reference purpose, but this way it is not stored as base relation onto computer storage medium. That follows to EMP underscore proj relation also. This also suffers from redundancy problem, hence EMP underscore proj is not used as base relation. This way it is not stored in computer storage medium. Otherwise it is obtained from employee, project and works on relations which are used as the base relations. They are stored onto the computer storage medium because they do not violate guideline 1 and hence free from redundancy problems. From them, by combining or natural join, this EMP underscore proj relation is obtained only for view purpose. So we have come to know that there will be redundant information in tuples if relations are violating guideline 1 and suffering from redundancy problems. So they will not be stored as base relations, but they will be obtained from natural join on the base relations which are redundancy free, which are not violating guideline 1. For example, employee relation, department relation, project relation, and works on relation. Okay, from these, by the use of natural join, that is combining related relations, we can obtain any view. For example, emp underscore dept or emp underscore proj. And emp underscore dept, emp underscore proj kind of relations, they also suffer from update anomalies. Anomalies means hidden problems. So update anomalies means problems that we come across while doing the operations like insert, delete, and modify operations. So the next topic is update anomalies. Anomalies are the hidden problems. Update operations means insert, delete, and modify operations. The problems which we come across while doing these operations, insert, delete, and modify operations, they are called as update anomalies. Next we shall see insert, delete, and modify anomalies one by one. The first one, insertion anomalies. So if you take emp underscore dept, which is violating guideline 1, so in that relation we have the attributes belonging to both employee entity type and department entity type. Suppose we are to enter the department related information. If employee has joined the company but not yet assigned the department, then null values have to be entered for department information in this relation. Okay, that is first one. It increases the number of null values in the relation. So if new employee details are to be stored and his department number is 5, his or her, so this department number related information has to be stored correctly. Otherwise, it will lead to inconsistent data. That is second one. So wherever department number 5 is there, that many times department information will have to be entered. And third one, if you take, if we have to insert new department information where not yet the employee has been assigned, then employee information has to be entered null, which is not possible because SSN is the primary key. Primary key value cannot be null. So these three are the problems here while doing insertion operation on relations like emp underscore dept, or it follows for emp underscore proj relation also. So for what points we considered that, if you see here in emp underscore dept relation, whenever an employee comes, so for that employee department information has to be stored. So if employee is not yet assigned any department and all the values have to be null, so it increases the null values in the relation. That is first point. And when employee information is stored, suppose if he belongs to department number 5, so many employees, in their details this department information has to be stored correctly. Otherwise it leads to inconsistent data. In one row, what department name and details we store, for the same department number in other rows also the same information has to be stored correctly. Otherwise it leads to inconsistent data. That is second one. Next, when a new department has been formed, if not yet any employee has been assigned, then there we have to store null. But for SSN we cannot store null, it is the primary key. That is the third problem. So these are the three problems related to insertion, that is called as insertion anomalies. Okay. Such insertion anomalies are not present in employee relation and department relation here, because they are not violating guideline 1, they are used as base relations. So whenever an employee information is stored in employee relation. So D number is stored here for that employee, which indicates the department number to which that employee works. Suppose if he is not yet assigned any department, only one null value can be stored here. No need of many null values here. So wherever 5 is here, that can be made null because those employees have not yet been assigned any department. So only few nulls are required. That is first point. Then when many employees are belonging to same department, their only department number is stored, but related department information, that is stored only once in the department relation here. It is not repeated multiple times, hence no need of correctly storing the department name in all the places. No problem of consistency here. That is second point. Suppose if any department is formed as new, not yet any employees are assigned, no need of storing any information here, hence no need of any null values. The problem of entering null value for SSN is okay. So insertion anomalies are overcome in relations like employee, department, which are not violating guideline 1. Okay. That follows to relations employee, project and works on in case of EMP underscore project relation. Then second anomalies, that is deletion anomalies. So if you take up EMP underscore DEPT relation, if we delete any employee belonging to a department, that is last employee belonging to that department, that information if we delete, we lose the information respect to department also. Okay, so this problem doesn't occur in the database of figure 14.2, means in case of relations which are not violating guideline 1. So here in EMP underscore DEPT relation, any tuple if you delete the last one, here only one tuple belonging to employee who works for department 1 which is present. If you delete this, we lose the department related information also. So that is deletion anomaly, which is not present in these relations employee and department. So if you delete any employee information here, last employee means only one employee information, that employee working for department number 1, only one is there. If you delete this, only employee information is deleted, but that department related information will be still maintained in department relation. So deletion anomaly is not present in such relations. Okay. Next we shall see to the third one, modification anomalies. If you consider EMP underscore DEPT relation, so if we change the value of one of the attributes, if we change the department name value, so that must be updated in all the tuples of all the employees who work for the same department. Otherwise database will become inconsistent. So that is what is called as modification anomaly. In EMP underscore DEPT relation, so an employee information is stored in a row here. That employee belongs to department number 5 and the department name is research DMGR underscore SSN. That manager social security number is 333445555. For any reason if this department name is changed, so that will be the department name of department number 5. So wherever department number 5 is there, so the department name has to be corrected, which should be same as this. Otherwise in multiple places multiple values for the same department name, that leads to inconsistent data. That is one. Second one, suppose DMGR SSN is changed. So manager of that department number 5, research department is changed. Then wherever department number 5 is there DMGR SSN must be stored correctly of the same value. Otherwise, in multiple places, multiple values for DMGR underscore SSN, that also leads to inconsistent data. So such kind of problems are called as modification anomalies. Such modification anomalies are not present in relations employee and department. So for an employee, the department number is 5 here. Department 5 details means they are stored in the department relation. That department name is research and manager SSN is 333445555. For any reason this department name is changed, it has to be changed only in one place here. No need of modifying in multiple places. Similarly, if DMGR SSN is changed, that has to be modified in only one place here, not in multiple places. Hence, no need of multiple modifications and no problem of inconsistency of data. So, such modification anomalies are not present in relations, employee and department. So, whatever anomalies related discussion we have done, that follows for employee, project and works on relations also, and for all the relations which are not violating guideline 1. Okay. And that completes the discussion on update anomalies. That is first one insertion anomalies, second one deletion anomalies, and third one modification anomalies. Seeing to update anomalies, guideline 2 is formed. It states that design the base relation schemas in such a way that no insertion, deletion or modification anomalies are present in the relations. Even if any anomalies are present, note them clearly and make sure that the programs that update the database will operate correctly. So this guideline 2 alerts for even if relation schemas are made to guideline 1, even then if any anomalies are present, they must be eliminated by the programs. That care has to be taken. Okay. So next observation with null values in tuples we shall consider. So if many attributes do not apply to all the tuples in the relation, we'll have more number of null values in those rows of data in a relation. So this null values, it will waste the space at storage level and it may lead to problems with understanding the meaning of particular attributes. And while doing join operations, it leads to ambiguity. And with null values, we cannot do the aggregate operations also. So when we do select and join operations that involve null values, the result may become unpredictable. So these are the problems with null values. Then storing of nulls. This have multiple interpretation, means null values have multiple meanings. For example, if you consider the attribute doesn't apply to this tuple, that is the first meaning. So if you take visa status, so for US students who are residing in US only, the visa status may not be existing. Hence this attribute doesn't apply to US students. So when it is not applicable, we will be entering null and that null indicates this is not applicable. That is first one. Second one, null value is entered when the information is not known. For example, date of birth attribute is there. For an employee, if it is not known, then null value will be entered. So here null value doesn't mean that it is not applicable. It is applicable, but it is not known now. So this is second meaning. Then third one, the value is known, but at present not available. For example, if you take home phone number for an employee, it may exist or may not exist. That only is not known. But even if it exists now, that value is not available and hence it is not recorded. So here the null value indicates whether that attribute value exists or not exists, we don't know. First one. Even if it exists, that may not be available, hence it is not recorded. So here null value is giving three kinds of meanings. In third one, again two kinds of meanings. So null is compromised with different meanings. That is why another guideline is stated, that is guideline 3. So as far as possible, avoid placing attributes in a base relation whose values may frequently be null. If nulls are unavoidable, make sure that they apply only in exceptional cases only and do not apply to the majority of tuples in a relation. For example, if only 15% of employees have individual offices, then we should not include this attribute office number in employee relation, because there may be hundreds of thousands of employees. Out of them, only few have office phone numbers. In remaining places, we'll have to enter nulls. So the relation will end up with too many null values. So in that case, better to have another relation called EMP underscore offices, in which attributes ESSN and office number can be created to include tuples for only employees with individual offices. No need of entering the employee SSN and office phone number for whom this number doesn't exist. Then there will not be null values. Okay. Next observation is with respect to generation of spurious tuples. Spurious tuples means extra tuples in the relation which are meaningless, which do not pertain to that relation. Okay. For that, as an example, consider this relation EMP underscore proj relation. It is having SSN, P number, hours, E name, P name and P location attributes. And these are the values which are stored in this relation. Okay. Now this relation is broken into two relations. This one relation is divided into two relations. Those two relations, relation schema, are EMP underscore logs, the attributes being E name and P location, both. And second relation is EMP underscore proj1. Its relation schema is shown here. SSN, P number, hours, P name and P location. Now the point is, if again we join these two relations on the common attribute, which is P location here, then we must get the original EMP proj relation. So we are taking EMP underscore logs relation and EMP underscore proj1 relation, and we are combining both the relations on attribute P location, and we hope to get EMP proj relation back. But if you see EMP underscore proj relation after join operation, these star marked tuples, they are the extra tuples which were not in the original EMP underscore proj relation. So these were not present in this original EMP underscore proj relation. So other than these, some extra tuples are there. These extra tuples, star mark tuples, they are called as spurious tuples, meaningless tuples, because they were not there in original EMP underscore proj relation. So EMP underscore proj relation was broken into two relations, EMP underscore logs and EMP underscore proj1. Afterwards, if they are combined on common attribute, that is P location, original relation should be resulted, but that is not happening. Along with original relation, some extra meaningless tuples are occurring. They are called as spurious tuples. They must be avoided. This is because P locations happen to be attribute that relates EMP logs and EMP proj1, and P location is neither primary key nor a foreign key in either EMP underscore logs relation or EMP underscore proj1 relation. So avoid we formulate one more guideline, that is guideline number 4. So guideline 4 states that design relation schemas so that they can be joined with equality conditions on attributes that are appropriately related, primary key, foreign key pairs, in a way that guarantees no spurious tuples are generated. Avoid relations that contain matching attributes that are not foreign key, primary key combinations, because joining on such attributes may produce spurious tuples. Means if at all if we join two relations, they must be joined on foreign key, primary key combinations. That completes the discussion on informal design guidelines for relation schemas and update anomalies. Next we shall move on to the topic functional dependencies. So the first question is, what is functional dependency, or define functional dependency? Functional dependency is a relationship that exists between two sets of attributes of a relation or table, where one set of attributes can determine the value of other set of attributes. It is denoted by X arrow mark with Y, where X is called determinant and Y is called dependent. That is, the value of X determines the value of Y. X is called as determinant and Y is called as dependent. The values of X component of a tuple uniquely or functionally determines the values of Y component, or we can say Y is functionally dependent on X. A functional dependency is a property of the semantics or meaning of the attributes. So examples for functional dependency are: SSN value determines the value of employee name. P number value, that is project number value, determines the values of project name and project location. Similarly, combination of SSN and project number value determines the value of hours. So if you consider EMP underscore DEPT relation schema and EMP underscore proj relation schema. So in this the functional dependencies are marked here. So in the first one, SSN value determines ename value. So SSN is the primary key. From there an arrow mark is going to ename. So this functional dependency shows that the value of SSN determines the value of ename. So that is what is marked here in the example. Okay. Next, if you observe here functional dependency 2, that is from P number attribute an arrow line is moving. So from here to P name and P location. So the value of P number determines the value of P name and P location. That is what is the meaning of this functional dependency 2. Another functional dependency, if you observe SSN attribute and P number attribute, from them together one more arrowed line is going to hours attribute. That means SSN attribute and P number attribute, both attributes values together determine the values of hours attribute. So SSN and P number attribute values both together determine the values of hours. Okay. So the above functional dependencies specify the value of employee social security number uniquely determines the employee name. That is this functional dependency. The value of a project number, that is P number, uniquely determines the project name, that is P name, and location, that is P location. That is this functional dependency. Next, a combination of SSN and P number values uniquely determine the number of hours the employee currently works on the project per week. That is this functional dependency. Okay. Next, we shall study what is meant by normalization of relations. So the next thought is if we have a large database in which we have single big relation, so that will result in data duplication. So the duplication of data may result in, so it makes the relations very large because simply many data is repeated. Then it is not easy to maintain and update data because multiple copies must be updated. It would involve searching many records in relation. So wastage and poor utilization of disk space is made. So the likelihood of errors and inconsistencies will increase. So instead of having large database having single large relation, it is better to have several small relations. So that is what is this means. So first let us know what is normalization. Normalization is the process of organizing the data and the attributes of a database. It is performed to reduce the data redundancy in a database, to remove update anomalies and ensure data consistency. Normalization divides larger tables or relations into smaller ones and links them using relationships. Why do we need normalization? So we need normalization to minimize redundancy. The main reason for normalizing the relations is to remove update anomalies. Failure to eliminate anomalies lead to data redundancy and can cause data integrity and other problems as database grows. Normalization consists of series of guidelines that help us to guide in creating good database structure. It helps to prevent data redundancy, improves data integrity, and simplifies data manipulation within a database. So in normalization, we have many types of normalization. The first one is first normal form, that is 1NF, then 2NF, 3NF. So 3.5NF or Boyce code normal form or BCNF. And apart from this, we have 4NF and 5NF, that is fourth normal form and fifth normal form. So starting from 1NF till 5NF, we have different normalization techniques. So normalization is aimed at organizing the data in a relation. Then for that, it may break the big table into several small tables or small relations. Its main aim is to reduce redundancy, to remove update anomalies, and preserve data consistency, and make query execution easier. Okay. As already mentioned, in normalization, there are different techniques of normalization or different types or levels of normalization. They are first normal form, that is 1NF, second normal form or 2NF, then third normal form or 3NF, next 3.5NF or Boyce code normal form or BCNF, then fourth normal form or 4NF, and the last one is fifth normal for 5NF. The definitions of each normalization form are: a relation is said to be in 1NF if it contains an atomic value. A relation will be in 2NF if it is in 1NF and all non-key attributes are fully functionally dependent on primary key. Means if there is no partial dependency. A relation will be in 3NF if it is in 2NF and no transition dependency exists. A stronger definition of 3NF, that is Boyce code normal form, that is 3.5 normal form. In that, the left side of the key should be a super key. Means the right side attribute values which are dependent on the left side attributes, they must be super key only. That is what is BCNF states. Make sure that every determinant is a candidate key. This is in another words. A relation will be in 4NF if it is in Boyce code normal form and has no multi-valued dependency. A relation is in 5NF if it is in 4NF and doesn't contain any joint dependency. Here in fifth normal form, the joining should be lossless. Let us see first normal form or 1NF. A relation is in 1NF if every attribute is a single valued attribute or it doesn't contain any multi-valued or composite attribute. That is, every attribute is an atomic attribute. If there is a composite or multi-valued attribute, it violates 1NF. So this is the definition of first normal form. So next we shall see what is the meaning of this with an example. Taking an example for 1NF, consider relation schema for department. The attributes are D name, D number, DMGR underscore SSN and D locations. This D locations is multi-valued. If you consider that department relation with the values are shown here. So D name value is research, D number value for that is 5, the manager social security number is 333445555, but this department is present in 3 locations, that is Bel Air, Sugarland and Houston. So D location attribute is having multiple values. This is multi-valued attribute. A relation in which there is multi-valued attribute, it will not be in 1NF. Okay, to bring it to 1NF, then for each value we'll have to write a tuple. So this is first value, for second value another tuple, for third value another tuple, these values being remain same for all the 3 locations. So the next tuple is written administration for MGRSSN and Stafford, that is here. Next tuple is written headquarters 1 and this MGRSSN and Houston here. But this part is having individual tuples for every value of this multi-valued attribute. So this relation now it is in 1NF, which was not in 1NF due to multi-valued attribute, that is converted to 1NF by adding a tuple for each value of the multi-valued attribute. Okay, this is how a relation which was not in 1NF, it is brought to 1NF. Here as such all the values were single valued, but only this delocation values were multiple. So delocation attribute was multi-valued. Now in 1NF when it is brought, so delocation values also have become atomic or single valued. That is what is 1NF or relation being in first normal form. Okay. Next let us consider another example for 1NF. This is a relation schema called EMP underscore proj. It is having another relation inside that. Its name is proj s. Okay. Its attributes are P number and hours only. But the attributes of EMP underscore proj is SSN, E name and one more nested relation. So that relation is shown here. So the name of relation is EMP underscore proj. So first SSN value, its name, but for one value here, 2 number of project numbers and hours are given. That means in this big relation, there is one more small relation. For SSN, 1, 2, 3, 4, 5, 6, 7, 8, 9 and employee name being Smith John B. If he is working on project 1, then number of hours is 32.5. If project number 2, the number of hours is 7.5. So this is an example for nested relation. When such is the case, then also it violates 1NF. Any attribute in a relation if you take, it should be having atomic values, not composite values or multiple values. Okay. Now this is a composite value. So this part is divided into 2. That is what is composite attribute. Okay, it gives rise to nested relations. Then the relation will not be in 1NF. The relation which is not in 1NF, because of nesting of relations where one attribute can be divided into two. It's a composite attribute here, but the attribute should not be multi-valued or composite one. Now this is brought to 1NF by breaking into two relations. This is first one and this is second one, in which nesting of relations is eliminated and the resulting two relations are in 1NF. Okay. Next, what is second normal form or 2NF? For a relation or table to be in second normal form, it must satisfy the following rules. The first one, the table must be in first normal form. Then it must not contain any partial dependency. That is, all non-prime attributes are fully functionally dependent on the primary key. A partial dependency exists when any non-prime attributes, that is an attribute not part of candidate key, is not fully functionally dependent on one of the candidate keys. If partial dependency exists, we can divide the table to remove partial dependent attributes and move them to some other table where they fit in well. In simple words, for a relation to be in 2NF, it should not contain partial dependency. Okay. Next, third normal form or 3NF. For a relation or table to be in third normal form, it must satisfy the following rules. The table must be in second normal form. Then, no non-prime attribute is transitively dependent on primary key. For each functional dependency, X determining the value of Z, for this at least one of the following conditions should hold. X is a super key of the table. Z is prime attribute of the table. A functional dependency X determines the value of Z is said to be transitive if the following three functional dependencies hold. X determines value of Y, but Y doesn't determine the value of X. Y determines the value of Z. If transitive dependency exists, we can divide the table to remove transitively dependent attributes and place them in a new table along with a copy of determinant. In simple words, for a relation or table to be in third normal form or in 3NF, it should not contain transitive dependency. Next, we shall see an example for both 2NF and 3NF. For example, consider this relation schema EMP underscore proj. The attributes are SSN, P number, hours, ename, pname and plocation. So this relation is not in 2NF. It is in 1NF because it doesn't contain multi-valued attributes and composite attributes. So after 1NF only we should go for 2NF. This relation is not in 2NF because it has partial dependency. So how it is having partial dependency, that we shall see next. Here if you observe in this relation schema, both SSN and P number attributes are underlined. Means both together form primary key. So these two attributes are called then prime attributes because they are the part of primary key. The other attributes, they will be non-prime attributes. So the non-prime attributes are hours, ename, pname and plocation. Okay. So if non-prime attributes are fully functionally dependent on prime attributes, then only we can say that there is no partial dependency. So if you observe functional dependency 1, so there SSN and P number together decide the value of hours. Means non-prime attribute hours is fully functionally dependent on both prime attributes, that is SSN and P number. Now there is no partial dependency in case of non-prime attribute hours. That is first point. Next, if you consider functional dependency 2, where SSN value, from there one line is going, that arrow is ending on here on ename. Now ename non-prime attribute value is dependent only on SSN attribute. So SSN attribute is the prime attribute and P number is also prime attribute, but non-prime attribute ename is not fully functionally dependent on both. It is dependent only on SSN. This is called as partial dependency. So prime attributes are 2, SSN and P number, both together form primary key. Non-prime attribute ename is not dependent on both, it is dependent only on SSN. This shows partial dependency. Hence, this relation is not in 2NF. Okay. If you extend the discussion, this P number that decides the value of P name and P location. P number is the prime attribute. This P name is non-prime attribute. P location is also non-prime attribute. That is dependent only on one prime attribute but not on both. So this also is an example for another partial dependency. Hence, this relation is not in 2NF. Okay. So in this relation schema, only hours non-prime attribute is fully functionally dependent on both the prime attributes. But the other non-prime attributes, ename is partially dependent on only one prime attribute. P name and P locations are partially dependent on only one prime attribute, that is P number. They show the examples for partial dependency. Hence, this table is not in 2NF. Okay. To bring this to 2NF, it is divided or broken into three relation schemas: EP1, EP2, EP3. EP1 is having the attributes SSN, P number and hours, in which hours non-prime attribute is fully dependent on both the prime attributes SSN and P number. So it is fully functionally dependent. There is no partial dependency. In EP2, SSN is the prime attribute. It's the primary key. Non-prime attribute ename is dependent on that single primary key attribute. So in the third one, that is EP3, P number is the primary key, it is the prime attribute. The other two non-prime attributes, they are dependent on this single primary key attribute. Now in these three relations there is no partial dependency, hence they are in 2NF. Okay. Now when partial dependency is removed, by dividing that table into three small tables, those are brought to 2NF. That is what is this is indicating. Okay. Next, let us see to an example for 3NF. For that, consider relation schema EMP underscore DEPT. Here the attributes are ename, SSN, bdate, address, dnumber, dname and dmgr SSN. Here SSN is made the primary key, that is what is underlined. Here in this SSN is the primary key, that is the prime attribute that decides the value of D number, which is non-prime attribute. It is okay, but this non-prime attribute is deciding the value of D name and DMGR SSN also. So these two are non-prime attributes. They are being decided by another non-prime attribute, that is D number. This shows transitive dependency. Here suppose if you take SSN as X, it's a prime attribute. It is deciding the value of D number, another non-prime attribute. So D number we take as Y. but y value decides the value of another non-prime attribute, that is d name. So this is z. Now x decides the value of y. Okay, this is prime attribute. But y is deciding the value of z. This is not okay because y is not prime attribute. When such dependency is there, that is called as transitive dependency. Hence, the relation will not be in 3NF. To check a relation for 3NF, first it should be in first NF. It is in first NF, there is no multi-valued attribute and there is no composite attribute. Then it is in 2NF because there is no partial dependency. But it is not in 3NF because there is transitive dependency. To eliminate this, the relation is divided into two relations. The first one is ED1 and ED2. So in ED1 we have attributes ename, SSN, bdate, address and d number. Here primary key is SSN, that is the only prime attribute. All remaining non-prime attributes are dependent on this. There is no transitive dependency in this. In ED2, d number is the primary key, that is the only prime attribute. All remaining non-prime attributes are dependent on this. So d number is the prime attribute now. It is not non-prime attribute. So other non-prime attributes are now depending on prime attribute. Hence transitive dependency is eliminated here also. Because no transitive dependency, these two relations are in 3NF. Okay. So the next normal form is Boyce code normal form or BCNF, which is also called as 3.5 NF. So this is advanced version of 3NF. It is stricter than 3NF. A table is in BCNF if every functional dependency we consider where attribute x value decides the value of attribute y. So x should be the super key of the table. Means this should be prime attribute. It should not be non-prime attribute to decide the value of another prime attribute. For BCNF, the table should be in 3NF and for every FD, LHS is a super key. For this, we shall see an example. So let us consider an example for BCNF. So considering this subject table. So it has three attributes: STUID, that is student ID, subject, professor. Here the conditions are each student can enroll in multiple subjects. Multiple professors can teach a particular subject. Means one subject can be taught by many professors. And one student can enroll for multiple subjects. For each subject, it assigns a professor to a student. So with this condition, if you take up this table, so according to these conditions, the functional dependencies first we have to identify. So in the given relation, if you check for existence of functional dependencies, there are two functional dependencies. The first functional dependency shows that here if you observe, this student ID is 2, subject is Java, professor name is Professor Anand. Okay. So here also it is Java, but to decide professor name, the student ID is also required. These two values decide this professor name. That is, both student ID and subject attribute values are required to decide the value of another attribute professor. So both these together form primary key. So this functional dependency, okay, both prime attributes together, they are deciding the value of another non-prime attribute professor. That is okay. But in functional dependency 2, this non-prime attribute is deciding the value of prime attribute because this is prime attribute here. So this non-prime attribute value is deciding the value of prime attribute. How we can say this Java is taught by whom? Professor Anand. This Java is taught by whom? Professor James. So here Professor Anand value is deciding this Java, and here Professor James value is deciding this subject attribute value Java, and hence this professor non-prime attribute value, this non-prime attribute value is deciding the prime attribute value, that is prime attribute subject value. This is not okay. Non-prime attribute cannot be used to decide the value of prime attribute. Hence, this is not in BCNF. This has to be eliminated. That is what is given here. LHS is not a super key. Left hand side is not a super key. This is not a super key. Super key means single attribute or set of attributes which are used to uniquely identify a row in a relation. Here to identify any row, the attribute values student ID and subject attribute values both are required. So these are prime attributes. So these together form super key. But professor is not super key. This professor attribute is not super key. LHS is not super key. And hence this is not in BCNF. Okay. Now to bring this relation into BCNF, it is decomposed into two relations. In one relation, student ID and professor ID are taken as attributes and both together are made as primary key. In second relation, professor ID, subject, professor attributes are taken and all the three together are made as primary key. So professor ID is the new attribute here. Okay. If you consider this example for BCNF where we have relation lots 1A. So FD1 functional dependency 1, if you observe, a line is going from property ID to country name, lot number and area. That is the value of property ID decides the values of country name, lot number, area. Here property ID is underlined also, that is primary key. Hence property ID is a prime attribute here. Prime attribute is deciding the values of other attributes, then it is acceptable. Next, if you observe functional dependency 2, the lines are going from both country name and lot number to property ID and area. So these two together form candidate key, means they also could be primary key. So they are also prime attributes. Both together they are deciding the values of other attributes, then also it is acceptable. But here the problem is in functional dependency 5 where arrow line is going from area to country name. Area is not prime attribute but it is deciding the value of prime attribute. That is, here the value of non-prime attribute is deciding the value of prime attribute. That is not acceptable. A non-prime attribute cannot decide the value of prime attribute. Hence, this given relation is not in BCNF. To bring it to BCNF, it is divided into two relations whose schemas are given here. Okay. So these two relations will be in BCNF because their property ID, area, lot number are the attributes. Only this prime attribute is going to decide the value of these two because this is primary key here. In another relation, here area is the primary key, that is the prime attribute, that is going to decide the only non-prime attribute here. In both of these, nowhere we can see that any non-prime attribute being deciding the value of prime attribute. Okay, hence these two are in BCNF. So this figure, if you see here, A and B together, they are deciding the value of C attribute. So A and B form primary key, they are prime attributes according to functional dependency 1. But according to functional dependency 2, a line is going from C attribute to B here. So B is a prime attribute whereas C is a non-prime attribute, because A and B together were forming primary key and hence A and B are prime attributes. They were deciding the value of another attribute C, then C is a non-prime attribute. But in FD2, this non-prime attribute C, its value is deciding the value of prime attribute B. So this represents this FD5, where area non-prime attribute, its value is deciding the value of prime attribute, that is country name. Okay. So if such dependency exists in any relation where a non-prime attribute decides the value of prime attribute, then that relation will not be in BCNF. C decides the value of B. C is non-prime, then it is not super key. LHS, when it is not a super key in any functional dependency, then that kind of relation cannot be in BCNF. Okay. This relation is in 1NF because it doesn't have multi-valued or composite attributes. It is in 2NF because there is no partial dependency. It is in 3NF because there is no transitive dependency. The next level that we have to check whether it is in BCNF or no, then we found that this non-prime attribute is deciding the value of prime attribute. So where a non-prime attribute is deciding the value of prime attribute and hence left side of the functional dependency being not a super key, and hence this relation cannot be in BCNF. To bring it to BCNF, it is decomposed into two relations in which there is no non-prime attribute deciding the value of prime attribute. That is why these two are in BCNF. Okay, that is all about BCNF or Boyce Codd normal form or 3.5 NF. Next we shall study fourth normal form, that is 4NF. Fourth normal form or 4NF states that a relation will be in 4NF if it is in Boyce Codd normal form or BCNF and then it doesn't have multi-valued dependency. For a dependency where X attribute value decides Y attribute value, if for a single value of X, if there are multiple values of Y, then the relation will be having multi-valued dependency. Then it cannot be in 4NF. To be in 4NF, first it should be in BCNF or Boyce Codd normal form, and then it should not have multi-valued dependency. This symbol denotes multi-valued dependency. Here attribute A, that is having single value but which decides the values of attribute B, it is having multiple values. At the same time, the same attribute A, which has single value, is deciding the values of attribute C, which has multiple values. The values of attribute B and C are independent of each other. Okay. A multi-value dependency occurs When in a table, for each value of attribute A, there is a set of values for attribute B and a set of values for attribute C, such that values of B and C are independent of each other. So that is what is denoted here. So this is exactly what we have to look for in a relation to check whether it is in 4NF, yes or no. Next, taking an example for 4NF, here we have EMP relation. It is having two multiple value dependencies. The first one, ename attribute, its single value is going to decide the multiple values of pname attribute. So that is what this is showing. So in the figure, if you see, ename attribute, its single value, that is Smith, is going to decide the multiple values, that is X and Y, of pname attribute. That is what is shown by MVD1 here. Second, multi-value dependency shows that the same ename attribute, its single value, decides the multiple values of dname attribute. So if you observe here, this ename, its single value, that is Smith, is deciding the multiple values, that is John and Anna, of dname attribute. Okay, so that is what is indicated by this second multi-value dependency. This relation is in BCNF because here no non-prime attribute is deciding the value of any prime attribute. That is first one. So relation is in BCNF. Next, this relation is not in 4NF because there are two multi-value dependencies. So to bring this relation to 4NF, it is divided into two relations. One is EMP underscore projects, another is EMP underscore dependents. Here ename and pname, both attributes are made as primary key. Both together are used to identify any tuple. In second one, ename and dname, both together form primary key. The values of both together are used to identify any tuple. This is how, by decomposing EMP relation, it is brought to 4NF. The final two relations are EMP underscore projects and EMP underscore dependents. These two are in 4NF. Okay. So next we shall move on to 5NF. Next, fifth normal form, that is 5NF. It is also known as project join normal form or PJNF. Okay. A relation is said to be in 5NF if following both the conditions are satisfied. The first condition is the relation should be already in 4NF. That is, the relation must not contain any multi-valued dependencies. Second one, it cannot be further non-loss decomposed. Means joint dependency should not be present. In another words, we can say that there should not be any possibility to decompose the relation into smaller relations with lossless joint dependency. Means the given relation, we must not be able to decompose it in multiple relations in such a relations that again if combined they should not be producing the same original relation. That joint dependency must not exist. So that is what is 5NF statement. In simple words, for a relation to be in 5NF, first it should be in 4NF and it cannot be further non-loss decomposed, that is it should not have joint dependency. Okay. Let us consider an example for 5NF. Here we have relation supply. It is not in 5NF. It is already in 4NF because it doesn't contain multi-valued dependencies. Now this relation is having joint dependencies. That is why it is not in 5NF. Okay. That means we can decompose this relation into further three relations here, that is R1, R2, R3, and when we natural join R1 with R2 and the result when natural join with R3, here we are able to get back the same original relation supply. That means lossless joint dependency is present in this relation supply, hence it is not in 5NF. That is why what relations it can be decomposed into, that is R1, R2, R3 will be the final answer, which will be in 5NF because they cannot be further lossless decomposed. Okay. So finally what we can say, the supply relation is in 4NF already. It is not in 5NF because it is having lossless joint dependency. That is why it is decomposed into three relations R1, R2, R3, which are now lossless joint dependency free. They further cannot be decomposed at all, and these are the final relations which are in 5NF. Okay. So that is all about 5NF. With that we come to the different normal forms, that is different levels of normalization. The first one 1NF or first normal form. A relation cannot be in 1NF if it is having multivalued or composite attributes. It cannot be in 2NF if it is having partial dependency. It cannot be in 3NF if it is having transitive dependency. It cannot be in Boyce code normal form or BCNF or 3.5NF if a prime attribute is dependent on non-prime attribute. It cannot be in 4NF if it is having multivalued dependencies. It cannot be in 5NF if it is having lossless joint dependencies. Okay. So to check whether a relation is in 2NF, yes or no, first it should be in 1NF, then only we can check for 2NF. To check whether it is in 3NF, first it should be in 2NF, then we can check for 3NF. To check for BCNF, first it should be 3NF and then we can check for BCNF. To check for 4NF, first it should be in BCNF, then we can check for 4NF. Whether a relation is in 5NF, to check for that, first it should be in BCNF, then only we can check for 5NF. So for this we have to observe whether a relation is having multivalued or composite attributes. For that we have to reorganize the relation or if necessary decompose the relation into several relations. Then it comes to 1NF. Further, if we eliminate partial dependencies, it comes to 2NF. If we eliminate transitive dependencies, it comes to 3NF. Then if you remove the dependency of prime attribute on non-prime attribute, then it comes to BCNF. Then if we remove multivalue dependencies, it comes to 4NF. Then if we remove lossless joint dependency, then it comes to 5NF. Okay. So summarizing normalization. Normalization reorganizes the data in a relation or it decomposes one relation or table into several tables. So why it is done? To minimize redundancy, to remove update anomalies, to maintain consistency of data, to make query execution easier. What are the 5 rules of normalization? Eliminate repeating groups, eliminate redundant data, eliminate columns not dependent on key, isolate independent multiple relationships, isolate semantically related multiple relationships. So with this normalization, we can have good quality of relations in any relational database design. Okay. With that we come to the end of discussion on chapter 14, that is basics of functional dependencies and normalization for relational databases. I hope you understood. Thank you.